Interesting about this question is that the right-hand side doesn't even look at an integer. That's a fraction. But it's actually true. We're going to prove it. So before we do, we already know the well-known formula of the dimension formula, where you only have two subspaces. Right? And the dimension of the sum of those two subspaces is equal to the sum of each dimension of each subspace minus the dimension of their intersection. So this is true. It's because, let's say we have V, and we have V1, V2. I have F, V1, V2. So that's their intersection, V1, V2. So first of all, we're gonna say the union, their intersection is also can be shown as a subspace of V. So as a subspace of V, we can choose a basis, right? Alpha 1 all the way to alpha k. So I'm assuming the dimension of, so as a base, V1 intersects V2. So I'm assuming the dimension of this is just k. Right? Then of course we want to deal with the V1. We want to find the basis of V1, right? So according to Steinitz substitution theorem, we can always expand alphas. Right? Then we have beta k plus 1 all the way to beta n as a basis for the subspace of V1. We can always expand it. Likewise, we can expand alpha 1 all the way to alpha k to gamma k plus 1 and all the way to gamma m as a basis for V2. Right? V2. So next, I'm going to show that alphas combined with the betas, combined with the gammas, they together form a basis of V1 plus V2. Right. So first of all, I have to show that they're linearly independent. Alphas, betas, gammas. So can I show that if I choose A1 times alpha 1 all the way to AK plus alpha K plus BK plus 1 times beta K plus 1 all the way to Bn times beta n plus CK plus 1 times gamma K plus 1 all the way to Cm times gamma m equals 0, where this 0 of course belongs to V, or 0 belongs to V1 plus V2 plus V3. So if I can show, of course, A's, B's, and C's all belong to F. If I can show that all the A's, B's, C's all equal to 0, that means the alphas, betas, gammas, they're linearly independent. Right? So starting from this, I can move this part on the right-hand side. Right? So A1 alpha 1, AK alpha K, BK plus 1, beta K plus 1, all the way, Bn beta n now is equal to negative of CK plus 1 times gamma K plus 1 plus all the way Cm times gamma m bracket. So notice that the left-hand side is a linear combination of the alphas and betas. Like I said, I've already expanded alphas and betas, right, as a basis of V1. So this part actually belongs to V1. belongs to V1. Right? So is the right-hand side. Right? We take out the negative sign, doesn't matter. Right? Still belongs to V1. Also, here is a linear combination of the gammas. Right? Gammas is a part of the basis of V2. So their linear combination has to belong to V2 as well. Right? So together they belong to V2, right? V2 as well. So belongs to V1 intersects V2. Right? So like I said, a basis of V1 intersects V2. This is a basis, alphas. So in fact, this can be, so like I said, I'm using only the positive part, right? Negative part doesn't matter because it's a subspace, right? So ck plus 1 times gamma k plus 1 all the way to cm times gamma m, it can be written as a linear combination of the basis of V1 union intersects V2, right? So D1 times alpha 1 all the way to dk times alpha k. The d's belong to F, of course. Then I just minus, right? Move this part to the other side, so it becomes minus. Minus, right? This side becomes 0. So here is a linear combination of the alphas and the gammas. Right? Alphas and gammas are basis of V2. Right? So therefore they are linearly independent. So equal to 0. So which means each C's and D's all equal to 0. D1. Right? Since all the C's equal to 0, right? So that means this right-hand side becomes 0. Right? So therefore, I have A1 alpha 1 plus AK alpha K plus BK plus 1 times beta K plus 1 all the way to Bn times beta n equals 0. So here's a linear combination of the alphas and betas. Right? Alphas and betas is a basis of V1. Right? They're linearly independent. So therefore, all the A's and B's must be equal to 0. And BK plus 1 must equal to 0. So overall, all the A's, all the B's, all the C's, all equal to 0, right? Given that their linear combination of alphas, betas, and gammas, if I let them equal to 0, then I say all the A's, all the B's, all the C's must equal to 0, right? Which means alphas, betas, gammas together, they are linearly independent, right? All the alphas together with the betas, together with the gammas, are linearly independent. Next, I want to show that these vectors form a basis of V1 plus V2. I've completed the first step. I've shown they're linearly independent. Next, I have to show that each element from V1 plus V2 can be written as a linear combination of alphas, betas, and gammas. Can I do that? Obviously I can, right? Because what's the meaning of V1 plus V2, right? V1 plus V2 is a set. Right? That set is made of what? That set is made of, you take any element from V1 and take any other element from V2. You add them up. Right? All the possible combinations, right? Put them in a set. That's the meaning of V1 plus V2. Right? Since every element of V1 can be written as a linear combination of the basis of V1, that's a linear combination of alphas and betas. Any element from V2 can be written as a linear combination of, right, the basis of V2, that is linear combination of alphas and gammas. Right? So when you add them up, it becomes a linear combination of alphas, betas, and gammas. So together, it's a linear combination of alphas, betas, and gammas. Right? So yes. So all in all, not only alphas, betas, gammas are linearly independent, but any element from V1 plus V2 can be written as a linear combination of alphas, betas, and gammas. Right? So therefore, alphas, betas, gammas together, they form a basis of V1 plus V2. So how many vectors are there? Alphas, betas, gammas, how many? Right? I believe it's you have k many alpha, you have k of them. Right? Betas, how many? N minus k. Right? How many gammas? M minus k. Right, together. So k minus n plus m minus k. Right? This is the number of vectors of the basis of V1 plus V2. Right? You have, right, that's the number. So that's the dimension of V1 plus V2. Right? So is it true? Yeah. So dimension of V1 plus V2. Right? And n plus m plus k, right? That's the dimension. That's the dimension of V1, right? That's the dimension of V2, right? Dimension of V1, dimension of V2 minus k. Right? K is the dimension of V1 intersects V2. Right? So this is really true. And now we are ready to prove our final result using the theorem I've just shown. Right? In the case of two subspaces, apply that to the case of 3. So even though we have some fraction on the right-hand side, right, what if we multiply by 3 on both sides? Right, then all of them become integers. So hypothetically, right, times 3. So left-hand side will become 3 times the dimension of their sum, right? So that motivates us to write the dimension of their sum in 3 different ways. Hopefully, in the end, everything will just cancel out, all become integers. So the fact that you saw V1 plus V2, V2 plus V3, V1 plus V3, right, reminds us of the fact that the sum of the subspaces is not only associative but also commutative, right, which can be easily shown. I'm not going to prove here, but dimension, we can rewrite their sum into dimension of V1 plus V2 first, then plus V3. And it's called associative, right? Change the order of sum, doesn't matter. It can be easily shown. And so apply this dimension formula, right? Treat V1 plus V2 as a whole entity. Right? V1 plus V2 can also be shown as a subspace of V as well. So dimension of V1 plus V2 plus dimension of V3 and minus dimension of V1 plus V2 intersects V3. Right? And of course, break down this dimension, right? Break that one down. We can rewrite into dimension of v1 plus dimension of v2 minus, of course, I'm going to copy this one down first, plus dimension of v3. Right, let's not forget minus dimension of v1 intersects v2. Right, copy down this as well. Minus dimension v1 plus v2 it intersects v3, no problem. Okay, then we're going to rewrite dimension v1 plus v2 plus v3 into dimension of, do v2, v3 first. Right, v2 plus v3. Right, associative. Again, apply this. Right? Treat this as a whole entity. Right? Dimension of v1 plus dimension of v2 plus v3. Then minus dimension. Of course, it's v2 plus v3. Right? Union or intersects v1. Right, so again, so rewrite this dimension. Copy it down, this one, plus dimension v2 plus dimension v3. We have to minus dimension of v2 intersects v3. All right, we're going to have to copy down this part. Minus dimension of v2 plus v3 intersects v1. And of course, dimension v1 plus v2 plus v3 can also be written into dimension of, I'm going to v1 plus v3 first, right? Then plus v2, right? Associative, commutative. So again, right, I'm just going to, right? Not getting too detailed, but following the same pattern, right? You rewrite those two, break them apart. You rewrite dimension of v1 plus v3, same formula. Right? So eventually you just have three different ways. Right? You add them up. You get 3 times dimension of v1 plus v2 plus v3. Right? Then you add up the right-hand side. Right? This part and this part. So you realize that. So this part is right. The dimension of v1 plus dimension of v2 plus dimension of v3. Here you have the same thing, right? And again, here you still have the same thing, right? Repetitive. And you also have something like this one, right? Also have something like this one, right? Just all the combinations, right? 1, 2, 2, 3, 1, 3, somewhere here, right? You have something like this, right? 1, 2, 3. 2, 3, 1. Somewhere here you have some, I don't know, 1, 3, 2. Right? All the combinations. Right? All of a sudden you have, right? Like I said, right? This is hypothetically multiplied by 3 on both sides, right? Right? So add them up, 3 times this one, right? So this times 3. Right? And of course, these are different. But once you divide by 3, right? Once you divide by 3, so they become one of them, right? One of those. And this plus that plus something similar to that, you divide by 3. So it becomes this. This. All the possible combinations of the intersection, right? Divide by 3. Likewise, this plus something else divided by 3, right? It's all the combinations of the sum and the intersection, right? Sum, intersection, sum, intersection, sum, intersection.